This conference will now be recorded.
So very good evening, students. We are discussing on standing waves on strings, normal modes, etc. So today we'll see a few important things related to normal modes, beats, etc. So which are very important in music industry and especially with the musical instruments, beats, then notes. So those terms are very important in that. We'll just learn something related to that thing. So as I was mentioning in the one of the previous classes, that all the musical instruments like organ pipe, violin, etc. are actually made of the made on the principle of standing wave. Okay, and in a musical note, not only a single frequency, there could be a number of frequencies which are called modes, normal modes, okay, or natural frequencies. Those things we'll be trying to understand. Okay, so this is the definition again, the definition of the stationary wave. And when two identical waves of same amplitude and frequency traveling in the opposite directions with the same speed and same in the and traveling along the same path and superpose each other, the resultant wave is called the standing wave, because that wave does not travel on either side in the medium, because nodes and antinodes, we have seen nodes means the position of maximum displacements. So we have seen nodes and antinodes. Nodes, positions of zero displacement of the material element of the medium. You can say medium also, or the elements of the medium. And antinodes, so nodes are generally denoted by n in the figure, and antinodes are denoted by capital A, and these are the positions of maximum displacement of the material element in the medium. Positions of maximum displacement. Okay, so we have even learned certain conditions. If you remember the analytical treatment, we had taken two waves, a sine omega t minus kx, and another one we have taken a sine omega t plus kx. Okay, omega t plus kx. So one is along positive x direction, traveling along positive x direction, and another one is traveling along negative x direction, and their superposition will give you the standing wave. That is what we have learned yesterday, and depending on that we have found out few conditions. Look in your textbook, in the NCERT textbook, this is altered. It is altered by this kx minus omega t. Actually, with the same meaning, we can have this expression also with the same meaning, kx plus omega t. So if you just take the summation, in this case, you will get 2a sin x sin kx, this as amplitude, and you'll get cos of omega t as the time dependent part. So in this case, if you want to have node, so in this case, this is the amplitude. So amplitude, the condition for the nodes and antinodes we should know actually. So with this expression of the traveling wave, anyway, this is just equivalent to the other one we have done in the previous class. So when you have your amplitude 2a sin kx, so positions of the nodes will be given by n lambda by 2. Okay, I'm sorry, this will be given as, yes, these are actually nodes. How? This has to be 0. So sin x 0 means kx has to be n pi. Okay, so n pi means k is 2 pi by lambda, so it will be n lambda by 2. Okay, so this is the condition for nodes. Okay, or condition in the sense positions of the node, positions of node. It will be exactly opposite to what we have learned in the previous class, positions of nodes. Okay, I'm just going with the NCERT textbook, that's why I'm just telling you this again. And positions of this I am writing positions of node, position of antinodes. So this will be given by again 2n plus 1 lambda by 4. So this is the position of antinodes. Okay, I'll just clean everything and then write the positions of antinodes and nodes. Positions of nodes are represented as n. So what are the positions? X is equal to n lambda by 2. Suppose this is equation number 1. And positions of antinodes are given by x is equal to 2n plus 1 whole into lambda by 4. Okay, this is equation number 2. All right, so these are the positions of nodes and antinodes. Now with this in mind, we'll just try to analyze the standing wave in a string. Standing wave in a string. Look, standing wave means standing wave string. In string, how you create? Suppose there is a stretch string having length L. The whole length is L, and it is fixed at two rigid supports. Fixed. This I have been telling you for last 2-3 sessions. Since it has a very like vivid example. This is actually a vivid example because in our normal life we do this kind of things. Okay, out of a practical example, it will be easier to understand what is standing wave. In fact, if you keep such a string and then like in this way, in this arrangement, and then plug it here in the middle and then leave it, you will see this kind of things. Okay, this kind of things you will see. Okay, if you have not seen, you can just try out once. All right, so suppose the string is fixed at two ends, and let us say the position here is x is equal to 0, and here it is x is equal to L. Okay, now if if someone is just give a strike, okay, just strike it or pluck it, as I said, pluck it in such a way that you just hold it like this, make a bow, okay, and then leave it and then see what happens. After plucking it, you just leave it, then you will see such kind of waves will be like modes will be created. We'll discuss what is called mode. Now according to our condition, if see reflection conditions, we know if these two positions are rigid or fixed, so here will be node, sorry, yes, there will be node, and at this position also will be node. So what is the condition at condition here to have a node? So this x is equal to, see, positions of node is in lambda by 2. So this L has to be satisfying, like has to satisfy in lambda by 2. Okay, this is the necessary conditions, and you know uh, this is the necessary conditions, and from here you can understand very easily that this lambda wavelength which is created, see, standing wave has a specific wavelength, so that wavelength also has some limitations, 2L by n. Okay, so this is the limitations. This wavelength also has some limitations, that is 2n by L. So if we say the uh, first one, suppose there are only nodes at the ends and there is only antinodes in the middle. If that is the case, then you look, then your L has to be sorry, lambda has to be 2L, equal to 2L. Your wavelength or your length of the string has to be half of the wavelength. Okay, that means you have to have a node in the middle. Okay, so this is the case. All right, so what we are trying to see is that, so L is equal to n lambda by 2. This is in general. Now you know, if T be the tension in the string, stretch string, small m be the mass per unit length, mass per unit length of the string, then the speed of the standing transverse wave, that is not the standing wave, okay, the speed of the transverse wave in the string will be given by V is equal to root over T by M. If you remember this, okay, V is equal to root over T by M. This is actually for a string. This is the speed of the transverse wave in a string. Okay, now look, if I write, so if I just try to find out how many frequencies and what like what are the frequencies, possible frequencies can be produced in the string, okay, frequencies, or how many waves, how many different waves will be created in the string. So we know L is equal to n lambda by 2. Now we know that v is equal to speed is equal to nu and lambda. So if we replace lambda with speed of the wave, transverse wave divided by nu, then we get L is equal to n by 2, and in place of lambda we'll write v over here and v by nu, so there will be nu here. Okay, so nu will be actually 2v 2v 2vl by n, or in other words, yes, so this is the actually so nu will be the frequency Okay, so here we can do another thing. Okay, so lambda is v by nu. All right. So frequency will be okay. Let me put this value of v over here. So it will be somewhere we have done some mistake. L is equal to n lambda. Let me just check once. L is equal to n lambda by 2. All right. L is equal to n lambda by 2. We put there n by 2. All right. Lambda will be okay. V will be up actually. Here we have done some mistake because L should come in the denominator. So V lambda, since lambda is up, so V will be here, nu will be here. So nu will be actually n, V is the speed divided by 2L. So this is the actual condition, or this is the general formula for the frequencies we obtain in the string. So there will be actually, see, the first frequency in the string we get is nu1 is equal to v by 2l, and if we put the value of v from here, then we get 1 by 2l root over t by m. So this is the actual frequency, the lowest frequency we get in a string when we vibrate. When the string is vibrating, there will be many frequencies, so which will be obtained. The frequency, different frequencies are given by this equation. Suppose this is equation number 1. So this equation nu is equal to n by 12 into v. This is the general formula for all the frequencies which we will be able to get, okay, in the string. So 1 by 12 root over t by m, this is the fundamental frequency or the first frequency. So this various frequencies are called modes, or various natural frequencies, whatever we get. So those are called modes of vibration. Okay, frequencies of modes of vibrations. All right, so I'll just write here. I have left some spaces over here. Okay, I think the heading is the old heading. I'll keep this much over here. Okay, so what we have got, the nu is equal to n by 2l root over t by m. Okay, and if we put nu is equal to 1, this is the lowest frequency or the fundamental frequency in the string. See, similarly we can get 1 by l. When we put n is equal to 2, so we get t by this root over t by m. then we can obtain many such varieties of frequencies we can have in the string. So this will be suppose 3, that means 3 by 2 L root over T by M. So like that we can have a series of frequencies with which the string can vibrate. So these are all natural frequencies. So these natural frequencies these natural frequencies with which the string can vibrate can vibrate are called natural frequencies or modes, normal modes. Natural frequencies are called, okay, so these natural frequencies with which the string can vibrate are called normal modes. Okay, normal modes. These are called normal modes. See, in the modes there are series of frequencies, so this is called series of frequencies, so these are called actually nodes. series of nodes so this each frequency is called normal mode, okay, or note, okay, normal modes or normal nodes. And see, the first or the lowest frequency of vibration of the string is called, okay, so lowest frequency of vibration is called the fundamental note or fundamental modes, called the fundamental mode or fundamental note, okay, and all the frequencies together are called series of notes, okay. So the lowest frequency, new one, okay, new one, it is called fundamental note or fundamental mode of vibration. And this fundamental mode is also, so these are even called harmonics also, harmonics, okay. With these natural frequencies are called normal modes, normal notes, or harmonics, okay, harmonics. So the lowest frequency is called the first harmonics. So this is the first harmonic, and then first harmonic or first overtone, also, first overtone, okay. New 2, that is the second normal mode, so that is called actually the second harmonic or second overtone, second harmonic. Like that, there are harmonics, many harmonics will be obtained, okay. So the general formula, I hope you have, okay, so you have learned already. So these are, so this is third harmonics. Like that, there will be different harmonics, and third harmonic or third overtone. Okay, so in general, string is vibrated in p segments, if it vibrates in p segments, then if, let me tell you one thing, if the string vibrate in n segments, okay, or p segments, then we can write the frequencies. Actually what I wrote, let me keep it the same with the n itself, vibrate in n segments, then frequency, this will be given by n by 2l root over t by m, okay, or see n is equal to, so nu is the first one, so nu 1 into n. N is integer number, it starts with 1, 2, 3, etc. So actually the other notes or other harmonics are actually integral multiple. Higher harmonics are integral multiple of the first harmonics. So higher harmonics are integral multiple of the higher of the first harmonic. Okay, all right, so this is with the string. Now we can just consider few things when we have already discussed the stretch string part. So let me tell you the law of vibration of stretch string. So what we have learned here, law of vibration law of vibration in vibration of stretch string of a stretch string. So we have already written down the frequency condition or the harmonics. Now from there itself we can just write down the law. Nu is equal to, we know, the n, if I write the general formula, n by 2l into root over t by m, where t is the tension in the string and m is the mass per unit length. Okay, now from here you can see, if I take the first one, nu 1, or the fundamental frequency 1 by 2l, anyway this is integer number, it does not matter with it should not come in the law. Okay, so look here, this frequency nu, anyway if I take this also nu also, so it is actually inversely proportional to the L. Again, this is actually law of length, this is law of length. I'll just, so there are three laws, mainly three laws here. So first one is law of length. Law of length. So frequency in the straight string is actually inversely proportional to the length of the string. Okay, the fundamental frequency of a vibrating string is inversely proportional to the length of the string for a given tension and mass per unit length of the string. The second is length of tension, law of tension. So what is the law of tension? We know from this itself, nu is directly proportional to the square root of T. That means the fundamental frequency of a vibrating string is proportional to the square root of its tension provided its length and the mass per unit length remains the same. When, here also we should write, when T and M constant, T and M remains same, Here when L and M remain same, okay, remain same. Okay. The third one is with obviously with the mass per unit length. So this is the law of mass. So these are three laws of vibration of a straight string. What is the law of mass? That is inversely proportional to the square root of the mass. Okay. The fundamental frequency of a vibrating string is inversely proportional to the square root of its mass per unit length, provided the length and the tension remain same. So this is mathematically, this is nu. Fundamental frequency means nu 1 actually. I'm just writing as nu 1 by m, square root of 1 by m. Okay. So these are three laws. Okay. Now the law can be again expressed in terms of density, in terms of diameter, if the string is having a certain density d, and if the diameter of the string is given. Okay, if the diameter of the string is given and density of the string is given, these laws can be written again. Another two laws can be again added. Law of diameter. If the mass per unit length is expressed in terms of diameter and the density, then fundamental frequency will be inversely proportional to the diameter, and law of density, since the mass is in the denominator, so density also will be this. Okay, inversely proportional to the square root of the density of the string if the tension and the length remains the same. Tension and length and diameter remains the same. All right, so this is about straight string. Now we'll discuss the normal modes in a tube with one end open. Okay, let me see the figure here. Okay, so in this case we have already learned when we are learning reflection. Here in fact the title will be different. for today's class. So if I have, see, this is actually a glass tube filled with some water. So this side is actually acting as closed end, and this part is actually open end. And we have seen when we have read about reflections. So if you have your end of the, like one end of the string, suppose if it is air column, here it is air column, obviously air column. So air column has certain pressure and density, etc. We know those things. And when this air column is actually vibrating, then there will be various frequencies of vibrations. Those are called normal modes or overtones or harmonics. So those we have discussed in case of string, but here we will discuss for air column created inside a tube, glass tube, opened at one end and closed at the other ends. How it is closed? See again. So not only closed, there is a level of water in the closed tube, and see this level of the water we can increase or decrease to control the length of the air column. So which we could not do in case of string, because if it is stretched, like if it is stretched between two fixed ends, then we cannot change the length. But in this case, the length of the air column can be changed. So this is actually, you'll be very much surprised that this uh, air columns are there in various instruments, and when we close a particular hole in fluids or somewhere, then we are actually controlling what we are controlling. We are controlling the length of the air column, and by controlling the length of the air column, we are actually producing various frequencies, so that there will be a sound which is very soothing sound, or that is called note. Okay, series of notes are created by controlling the length of this air column. All right, we have already learned that this open end there will be antinode, and at the close end there will be nodes. Okay, nodes. All right, there will be a node over here and antinode over here. So from the condition of nodes, we can write actually and find out the frequencies. In this case, you look, in case of close end, see the condition position for node will be annual n lambda by 2, as we have learnt already. And if the air column has length L, then this L has to satisfy this condition to get the node over here. And see from here, similarly actually we will get uh, condition for antinodes also. So nodes are here, positions of the nodes will be actually given by L is equal to n lambda by 2. This is the condition. So what are the lambda or the wavelength, possible wavelength which will be produced here? This is the case 12 by n. So this is the limiting value of, like this is the general formula or general value for all the wavelength which could be excited in this air column, within this air column. So we can put L is equal to lambda 1, that will be 2L. Okay, n is equal to 1. Then we can write lambda 2 will be obviously L, lambda 3, then it will be L by 3, etc. Okay, so these are the wavelengths we can excite. Okay, now we know that the speed in case of air, like in air, what is the speed of sound? Speed of sound is given by gamma p by rho. If you remember, I have already discussed. P is the pressure in the air column, and rho is the density in the denominator. Gamma is the Cp by Cv. Cp by Cv is the gamma. Okay, gamma for gas or air. Okay, so all right. So this is the velocity of the sound. Actually, here the sound will be created is the um, longitudinal longitudinal wave will be created, not the transverse. So this the speed of the longitudinal wave will be given by square root of gamma p by rho. Now if we go to find out the frequency will be always v, velocity by lambda. Okay, so suppose this is nu n, so v by lambda n, because all the waves will be having the same speed. That's what the idea is. In case of standing wave, because here nodes antinodes are created, means there are standing wave. Okay, so v, we know v is this one, so frequency will be v by lambda n. So what is lambda n? Lambda n we have got, okay, v by lambda n. Lambda n we have got 2l over n. Okay, so we can write n by 2l square root of this v will be using gamma p by rho. Okay, n by 2l square root of gamma p by rho. So this is giving you the general formula for having various frequencies present in the oscillations created in the air column within this kind of glass tube, where one end is closed, another end is open. So in this case, you look, if I write the fundamental frequency or the fundamental mode, normal modes, or the first harmonic or the first overtone can be written as 1 by 2l square root of gamma p by rho. Okay, so this is the first overtone or the first harmonic or fundamental frequency, fundamental mode. Then you will get, if I write n is equal to 2, then you will get 1 by l. 1 by l square root of gamma p by rho. Okay, so you can see this is actually the twice of the fundamental frequency nu 1. So that's why this is actually first harmonic, this is second harmonic. Okay, second harmonic, like that. And if I write 3, then 3v by l, or 3v by 2l, or 3 into nu. So these various modes of vibrations of an open pipe are actually shown over here. You can see that in this. So this is the fundamental one, or the first one, and this is the third harmonics. This is the fifth harmonics. Okay, okay, so here you can see, you can look one thing. So this is the whole thing with the, see, this is one node, another, here it is node, and this is antinode. So node and antinode, so between one node and antinode you will have, this is node and antinode. So this is actually lambda by 4, lambda by 4. So this is actually lambda by 4 has to be equal to l. or yes, lambda has to be 4L in this case. Okay, lambda has to be 4L. First case. So yes, so yes, so in case of second, what you should have in the first case, see here itself, lambda will be 2L, 2L, okay, 2L. I'm sorry, this will be 2L actually. Lambda is equal to 2L. I'm sorry, this will be lambda is equal to 2L, and 2 will be lambda is equal, lambda 2 is equal to L. So in this case, actually, this is all right. This is lambda by 4 itself. This is lambda by 4. So the whole length is lambda by 4. Okay, whole length is lambda by 4. If you want to get lambda, then it has to be 2L. This is lambda by 4. So if you want to get lambda, the 2L has to come. Another 4 lambda by 4. I'm sorry, this is lambda not and lambda by 4 itself. Okay, so in this case, we can check the third harmonics. In case of third harmonics, look, you can write this is x is equal to here for first harmonic, this is x is equal to L. So here x is equal to 0 suppose, then there will be an antinode with this third harmonics. This will be L by 3, then it will be 2L by 3, then it will be actually L. In case of fifth harmonics, this will be L by 5, then it will be, this will be 2L by 5, then 3L by 5, 5, 4L by 5, and this will be L. Okay, this is how the segments, different segments, at different segments, you can in fact find out the expression for the positions where different modes will be, like where nodes and antinodes will be seen. Okay, so we'll just quickly go to the normal modes in a tube when both the ends are open. When both the ends are open, okay, so just a minute. Actually, just a little bit of clarification in this case. So what we have discussed so far is actually for the modes in open organ pipe, in both side open. Okay, let me just repeat the clarification over here. So what is the clarification we have just taken? L is equal to n lambda by 2. This is the condition for the nodes. Okay, but we should have taken here condition for the antinodes, because at this open end, this end, I'm just taking x is equal to 0 over here, x is equal to L over here. So we have to take condition for antinodes. Okay, this is the clarification for this. and otherwise whatever we have discussed, also there will be a little bit of clarification. So this is the condition for the lambda by 2. Just keep patience, I'll just clarify you what we have done. We have done a little mistake here, because nodes are created at this place, not here. So they are anti-nodes. So we have to take the condition for anti-nodes. Lambda by 2 over here. So the condition will be actually 2n plus 1 lambda by 4. Okay. So that's why we had a little bit of confusion while I was telling you the length along with the lambda. So see, the fundamental wavelength has to be 4 into L. So this part is actually the wave. So lambda by 4 we are seeing here. In this actually we are seeing lambda by 4. In this particular length we are seeing 1/4 of the wave. 1/4 of the wave. Okay. So this is the fundamental mode. So fundamental mode, and if I see the third harmonics, so what will be the third? N is equal to, when you put n is equal to 0, that is the first. So n is equal to 1 is equal to second, n is equal to 2 is the third. N is equal to 2 means you'll get 5 into lambda by 4. So this is the third harmonics. So in this case you look third harmonic. Okay, n starts with 0, 1 and 2. So this will be 2. N is equal to 2 means 5 lambda by 4. 5 into lambda by 4. This should be the length L. Okay. So in this case, you see there will be 4 quarter, like fifth quarter. So this is 1/4 up to here. Then it will be another up to here. This, or we can say this is the whole lambda by 2. This is lambda by 2. And this is lambda by 2 plus lambda by 4. Okay, lambda by 4. So this will give you 3 by 4 into lambda. This is third harmonics. N is equal to 0 is the first, n is equal to 1 is the, I don't know, there is some mistake over here in this. Third harmonics should be, yes, this is called third harmonics. Lambda by 2 plus lambda by 4. So this should give you 3 lambda by 4. So this is 3 lambda by 4. Yes. So this is 3 lambda by 4. Okay. But we are getting third is fifth. This should be 1. N should be 1 for third harmonics. Obviously we will get the, see, the harmonics we will get in closed pipe, since this is the 2n plus 1 divided by lambda by 4. So we'll get when n is equal to 1, so we'll get L is equal to, okay, first is lambda by 4, then it is lambda if I put n is equal to 1. All right, there will be sum off, obviously, yes. So the first harmonic will be off over here. That's why the this is the fundamental, sorry, the fundamental second harmonics will be off. You'll get odd harmonics. That's why my confusion was. So you'll have odd harmonics. So n is equal to 1. So this is n is equal to 0. That is the fundamental harmonic, fundamental one. So when we put n is equal to 1, this is actually, this gives you the third harmonics. because their odd harmonics will come. Okay, after the fundamental one, you'll get the odd harmonics. Okay, the higher harmonics are actually odd harmonics. Higher harmonics, yes. So this is the confusion we had. So higher harmonics are odd harmonics. Like we'll have first, then we'll have third, then we'll have fifth harmonics, then seventh harmonics, like that. Odd harmonics will be getting odd harmonics. So n is equal to 1 means 3 lambda by 4. Then n is equal to 2 means there will be 4 by 5 into, so 5 lambda by 4. So this is how you look. 5 lambda by 4, this is the fifth harmonic. Okay, so in fifth, see, how do you remember which one is what? So there will be, see, this is the integral multiple. Lambda by 4 is the lambda by 4. Lambda by 4, lambda by 4 is the fundamental one. So lambda by 4 into 3, that means this is third harmonic. Lambda by 4 into 5, this is the fifth harmonic. Okay, so we'll have the odd harmonics in case of closed pipe. Okay, which we had actually had a little bit what to say. This is the clarification I just wanted to do with the closed tube. But what we have done in case of open pipe, see, in case of open pipe, both sides are actually antinodes. Okay, both sides you will get antinode. At x0 is equal to 0 also, at x is equal to L also you'll get antinodes. So you can actually get all the harmonics in this case, and the frequency you will get, if you write the condition for frequency, so you'll get n v, this is v by 2l. Okay, n v by 2l, this is the condition for the normal modes. Okay, this will give you the normal modes we get in case of open pipe. So we get here all the harmonics. So all the harmonics you will get, all the harmonics. We get all the harmonics here. Like, see, new one you will get v by 2l, as we were discussing so far, gamma p by rho. New 2 will be v by 2v by, again 2v by 2l, so you'll get 1 by l root over of. This is the case with open pipe. So in case of open pipe, you will get all the harmonics. So you will get first, second, third, fourth, all the harmonics you will get. But how the nodes and antinodes will be created? What are the length? Let us say x is equal to L. This will give you n lambda by 2, n lambda by 2. So you should have lambda is equal to 2l by n. Okay, so okay, let me write this itself. So when you have the fundamental mode, see, within the length L, you will have half of the wavelength. Within this L, you will have half of the wavelength. So this is C, this is node, this is antinode. So this is lambda by 4. This is also lambda by 4. As a whole, you will get lambda by 2. Now see, in the second case, second means it is L is equal to lambda. L is equal to lambda. That means, so this is see, between two nodes you will have lambda by 2. So here lambda by 4, and here also lambda by 4. So you get total lambda over here. Okay, In case of third harmonics, you can see third means you should get L in the within the length L, you should get 3 by 2 lambda. Okay, that means lambda plus lambda by 2. So you look, you will get, this is, see, node, node, antinode, node, antinode. So you will get, this is one whole lambda, this is whole lambda, this is lambda by 4, and this is also lambda by 4. So you'll get ultimately 3 by 2 lambda within length L. Okay, so this is how we can analyze. So what is the conclusion of this today's class? Conclusion is, okay, bit and all I'll discuss again in the next class. Okay, bit I'll discuss in the next class. So what we have learned from today's class is, in open pipe in the sense open in both sides. Okay, in open pipe we get all the harmonics, but in closed, or in the pipe one side closed, or but in the pipe one side closed, in the pipe one side closed will have only odd harmonics. Okay, we'll have only odd harmonics. All the odd harmonics. Okay, and what is the condition for open and closed pipe? We have already written down. So in case of open pipe, nu will be given by n by 12 into v, that is the velocity. V and nu both are looking like alike, so let me write, this is nu is equal to n into v by 12, and in case of this is open pipe, and in case of closed pipe, this, let us say n, nu n, this will be 2n plus 1 by, okay, this is into v by 4l. Okay, so this is the case, by 4l. So from here we'll get all the odds. This starts from n is equal to 0, 1, 2, 3, etc. And for this, n is equal to 1, 2, 3, etc. Okay, so this is for closed pipe. Let us say this is a closed pipe. That means one side is closed. Okay, or pipe one side closed. Okay, we'll stop it here for today. If you are confused, tomorrow we'll repeat this again a little bit, and then we'll discuss about the bits frequency and analytical treatment, and we'll take a few numerical examples on this particular topics, like normal modes in various cases like strings, or in open pipe, closed pipe. All those things we'll discuss again tomorrow once again with numerical examples. And before that we'll discuss the bits also, and finally we'll finish this chapter in another 2 classes maybe, with discussing with the discussion of Doppler effect. Okay, so bye for today.